You probably know all that, but I felt I should say. Okay, now, I put up the solutions to the quiz. Did y'all see them, everybody? I will be happy to go over that after I cover we did the TM mode, right? I want to do the TM mode. First, did you have questions pertaining specifically to the homework I gave you for last class? Anything else? It's just straight number crunching, huh? For the mode numbers. I'm going to say this. Here's things, it doesn't matter if it's TE or TM mode, it's always true. The cutoff frequency, all right, and it'll have Mn as the indices, it'll always be integers, is always 1 over the square root of mu epsilon. That's the velocity of light, divided by 2 times the square root of m over a squared plus n over b squared. Now, this is the cross-section of the guide. A will always be there on the lower part. It is the horizontal dimension, and it's the widest dimension. And B is the vertical dimension. And this is, again, a very long one. So when you look at this, these are the cutoff frequencies. And what they mean is, if you're not at that cutoff frequency or higher with the excitation frequency, nothing propagates. Somebody sent me a message I should bring a waveguide. I apologize, I didn't bring them in. I will bring them. They're just long metal pipes that are rectangular. That's all they are. How many have seen waveguides? If you have, how many have a microwave? Your microwave has a waveguide, right off the actual power source there. It's the microwave power source, which is usually, I guess, a cyclotron in your case. It will feed right into the chamber, and it's impedance match. It's a rectangular guide, promise you. You can look and see these things. But anyway, the way they're actually fed waveguides, this will be a plate of metal back here, and then they'll cut a little hole right there, and they'll put a filament down here. Now, the filament and antennas we haven't covered, but that antenna will be impedance matched to the guide impedance. Do y'all follow me on that? And it will be an efficient way of coupling energy. It's just like a coax cable, only it's at much higher frequencies, and that's the reason we use waveguide, not coax, because coax simply is too inefficient. You lose too much power at these frequencies, for microwave frequencies. Okay, class? Those are cutoffs. You have to be above that frequency to actually propagate. So we did TM. And for the TM case, you remember the electric fields in the z direction are the basis for all that, and they're equal to some E naught. That's a scalar value. This is in your book. And it's times the sine of m pi over ax times the sine of n pi over b y, right? And then it's times e to the minus j beta z times z. Now in Whitworth's book, he'll just have beta. And beta, this is for the TM mode, this is the one we did. Beta sub z, which is Whitworth's beta, is equal to, and I'm just going to give this to you. I could put down several different forms of the equation, but here's the one that's used almost, well, I say almost always. This is the form I gave you. I'm going to show you how it actually breaks down. It was omega squared right here times mu epsilon, and then it was minus, and over here it was m over a squared plus n over b squared, square root of that. Do y'all remember that, class? That was in the notes. If you, I forgot. Yes, sir.
In the notes, I have that as m pi.
Oh, yes. I'm so sorry. You're absolutely right. This isn't the form we're going to use. I factored out the pi later. Yeah, but for the cutoff, you're absolutely right. This isn't the form we use. I'm going to show you the form we use. Now, y'all see right here, before I'll let you catch up. I just want to tell you what I'm thinking. I know omega is 2 pi f, right? I know there's pi's here. They're all squared, right? I can pull out, if it's pi squared square root, I can pull out pi. Y'all agree with that? Y'all can see that I probably can do a few things to modify this. when everything is said and done, and I could go through this, but it really won't help, what you end up with is this. You have beta in the z direction is equal to, and this is really going to be beta, or it will be omega squared times square root of mu epsilon. And then it's going to be times the square root of 1 minus f over fc squared, or I'm sorry, fc over f squared. I'm going to explain something about this. What usually is done is we call beta unguided omega squared, or sorry, omega, pardon, times the square root of mu epsilon. And I have omega squared. This is actually omega times square root of mu epsilon. And then they introduce a term that is called k. And k is equal to the square root of 1 minus fc over f squared. I'm going to comment about this, and then they finally get the final form of beta z here. And that's simply beta unguided times k. But I have to make some comments, because some of this is new to you. Remember, as engineers, we like to take things and make them simple. Anytime we can reduce something to a single constant or value and just use that, we do it. So this is something that occurs all the time. Now, the operating frequency is not going to change per se, and FC has to do with the mode numbers and the dimensions of the guide. You see how FC here, it depends on the mode. If it's a 1, 1, M and N are the mode numbers. This will become clearer as we go on. M and N are like 0, 1, 2, 3, 4. Y'all with me? You cannot have a 0, 0 mode, period. That's something that makes no sense. Nothing's happening. The lowest possible mode we'll see will be the TE10 mode. And I'll get there, but for the TM modes, the lowest possible mode is the 1, 1, because here, neither one of these sine functions can be 0. If M or N were 0, then the argument of the sine function would be 0, and then you'd have nothing. Y'all follow me on this? For a TM mode, the lowest possible mode numbers are 1 and 0. A question you probably have is, so what do these mode numbers tell us? The real thing they tell you is how the electromagnetic field's distributed inside the guide. The higher the mode number, the more changes you have, like over the dimensions of the guide. Now, I'm going to try to say this in a way that will be meaningful to you. You all know that this waveguide really works as a high frequency filter, right? And it's something you probably know from acoustics is like when you hit a bell, it rings at what's called a resonant frequency. Y'all know that, class? Has to do with both the stiffness of the material it's made of and the relative mass density. Now, I'm not going to write the second order equations and solve, but at least have an appreciation for that. Well, the way this works inside this waveguide is this. The electromagnetic fields in the vertical direction, for instance, they have to either be something that has to be 0 here, has to be 0 here, and they have to solve Maxwell's equations, which mean it will be sinusoidal or cosinusoidal. Just appreciate this. This, the lowest order possible mode, is when this dimension is a half wavelength. Just appreciate that for now. The next order mode cannot occur until the frequency is high enough so you get a full sine wave there. You all follow? Which would be twice the frequency of the original. The next mode will be when you get basically 3 humps. 2 up, 1 down. You all with me? Now, these things, those are the modes. If you're above the first order mode, but you haven't hit the second mode that's allowed, then only the first order mode fields will be actually developed, if that makes sense. All right, the field mapping will be first order. If you go beyond say there's the 1-0 mode and the 1-1. Once you go beyond the 1-1 mode, you have no way of knowing how much energy or power will be in the 1-0 and how much will be in the 1-1. At least you don't know. Do y'all follow me in this class? So again, what we usually do with a rectangular waveguides, we operate it just above the 1 mode, but this will come later. I'm just telling you this to give you perspective and appreciation for why we're doing this. So if you look here, this K value appears here, and I want to give you the next value. And this is true, doesn't matter if it's TE or TM, this is generally true right here. So this is true for TE and for TM. That's K, that's beta unguided, that's beta Z, okay? Another thing is the phase velocity. Remember I was telling you about phase velocity? In general, it's omega over beta. For our case, it's omega over beta Z. Now here's what's really happening. What is the phase velocity in a lossless media unbounded? Isn't it 1 over square root of mu epsilon? It's the same as what? Group velocity or velocity of energy, right? Well, what we do here, we could write off this equation. I'm just going to show you what you can do. I can take this. You can see that beta Z is beta unguided or that, and you can see the omegas cancel. Y'all with me? Because look, beta unguided here, right? That's omega squared and mu epsilon times K, that's K. What really happens is this becomes the phase velocity. Well, I'll put it down as 1 over square root of mu epsilon first. It's 1 over the square root of mu epsilon, and then it's divided by K. Everybody follow me? Please listen to this. Now that value of K has to do with the operating frequency F, and it has to do with the cutoff frequency of the mode number. Do you all follow me? Almost always that cutoff frequency will be the 1 mode, just to make sure. I mean, it doesn't have to be, but almost always in the real world. Now, if you look at this, what's this value as you get close to FC for K? Make them equal. What happens when FC equals F? That becomes 1. 1 minus 1 is?
0.
0, right? 1 over 0 is? Infinite, right? 1 over 0 goes to infinity, doesn't it, class? You all see how the phase velocity is approaching infinity as you approach cutoff frequency, class? Can you all see it here, mathematically? Now here's what's really happening in a waveguide. Before I get to the T, so you can appreciate. You've got a phase front. Wentworth's book kind of shows you this. It looks like this. This phase front is moving this way. It strikes there, then it's moving down, now it's moving this way. You all follow me? All right? Now, the position that this phase front intersects this waveguide wall and moves in this direction is the actual phase velocity. Remember I told you about ocean waves striking a beach shore and how where they're actually striking the shore is like the phase point that's moving across the shoreline. You all follow me on that? Now look at this. If this is the ocean wave coming in and it's hitting in that direction, if the wave is going 10 meters per second this way, well, that actually intersecting point is going much higher in velocity. And you can see as this gets shallower and shallower and hits, even a small movement here is a large movement in where that intersection is. So the phase velocity can go to infinity. As the frequency gets higher and higher for a given mode number, here's what happens. Then there's less and less bouncing this way, and it's more straight. All right? It's more like a plane wave move. In the limit, as frequency goes to infinity, it's as if the velocity in free space for a given mu epsilon is the same as the velocity in the waveguide. Just keep that in mind, okay? Higher the velocity, the more direct the energy is flowing. The phase velocity approaches the velocity of the wave in free space. Now, there's something else I got to tell you. This is true for both TE and TM modes, by the way, what I'm showing you. That's the reason I put that. The group velocity is the velocity energy travels. That's the important one to you and me. The actual group, this is phase velocity. Group velocity, I like to call it the velocity of energy flow. V group, right, is really equal to simply the velocity, really I'll just call it the phase velocity, I'll call it 1 over mu epsilon. Now that's like the actual free space velocity squared divided by the phase velocity. And really what it boils down to, it's the square root, or 1 over the square root of mu epsilon times k. So now that one's proportional with k. You can see that k, as you get close to the cutoff frequency, is about 0, right? K goes to 0 here. When the cutoff frequency goes to, when f goes to the cutoff frequency is near the cutoff. Which means that the actual group velocity, this is the velocity of energy, it's called v sub g, or group. How many remember group velocity? You all remember that? Or velocity of energy? You remember phase velocity from physics? Physicists usually really make a big point. Phase velocity is different than group velocity. Group velocity has to do with the velocity energy moves. That's the one that's important to us, right? We'd like to know how fast we can get energy down a tube. Well, you can see you get no energy down the tube when you're at the cutoff frequency. And what really happens is the wave ricochets off the top and bottom. Nothing flows. Then, as you get higher and higher frequency, now the group velocity, now you're moving energy down the tube, or power. And that's real important to appreciate as engineers. Because engineers in the field have a nasty habit of mixing things up like that. And so they design a system to get energy down at a certain rate, but or power, and if it's based on the phase velocity, they get nothing, they don't know why. Or everything's off. So just appreciate this stuff. All right. That stuff there I'm showing you, that works for either mode. Remember that. Now I'm going to do the TE mode, and I'm going to try to do this fairly direct. This is, that's TM field. These are true. Everything here down is true generally. That, and that, okay? Now I'm going to do TE, and then I'm going to show you wave impedance. And I'm trying to show you things that are real important when it comes to real waveguide engineering. Wilmer's book doesn't have much on this in terms of real world problems. His are more or less, I guess, just to familiarize you with them. I mean, his book, they ask for mode value. I mean, the actual 5 lowest modes that will travel in terms of the cutoff frequencies and stuff. But that doesn't really help you with solve a real world problem. So next, we do the TE mode. When we do the TE mode, first we have to define it. Well, the transverse electric simply means that E in the Z direction is 0. All right? The entire electric field is perpendicular to the direction Z. Y'all follow me? So when the wave is bouncing, it's like the E field's this way. If that's the Z direction, it's bouncing like this. There is no E field that has a component in the Z direction. Y'all got that, class? So it's called TE, or transverse electric mode. Usually it's, I like this, I see it this way. You'll see the E field, and if it is a TE mode, they'll do this to say it's perpendicular. It's transverse electric, but it doesn't matter. I'll spell it out for you. So for this mode, now, you remember the equation before I had was, you don't need to write this down, del squared of E Z, right? And then it was plus, really omega squared mu epsilon times EZ equals 0. Well, that's assuming there's an EZ field in the Z direction. That was for TM. For our case, there is no TM. This equation is not for TE. For TE, you get del squared of HZ plus omega squared mu epsilon HZ equals 0, okay? So, doesn't that make sense? If there's no E field, there's got to be an H field, right? In the Z direction. This is the one we solve, and it's a very interesting solution. You use separation of variables, and you assume a solution. Some of this stuff will bore you, but at least you should be exposed, because somewhere down the line you're probably going to have to revisit this. If you do anything that has to do with material science application to fiber optics, waveguides, power transmission, Wi-Fi, you're going to see this over and over, so you should be exposed and familiar. what they normally do is say, let hz be a function, just x of x as before, y of y times z of z. Alright? Then I take this and I do the usual expansion in Cartesian coordinates, second derivatives, just as before. When I do that, I get the second derivative of 8z with respect to x squared plus the second derivative of 8z with respect to y squared plus second derivative of 8z with respect to z squared plus, and what I'm going to do is put it here, omega squared mu epsilon 8z equals 0. That's just expanding that. Remember how I did that last time for TE? Bored you, but at least you remember, right? Next step is I put this in here, and this becomes x double prime yz. This is going to be x y double prime z, and this is x times y, right, times z double prime plus omega squared mu epsilon x y z equals 0. These are all the capital, these are functions just of x, y, or z. Do you remember what my next step is? What do you want?
Divide by x, y, z.
Yep. Divide the whole thing by the functional form of x, y, and z, correct? Capital X, capital Y, and z. How many remember that? Okay. So when I do that, now I get x double prime over x plus y double prime over y plus z double prime over z plus omega squared mu epsilon equals 0. And probably it's wise at this point to introduce the beta unguided equals omega squared mu epsilon, and then I can take this omega squared mu epsilon and just replace it by beta unguided squared. You all with me on this? Anybody for the next step? You're absolutely right. Some of you remember. Couldn't hear you.
Oh yeah, which equation of those like do we actually need? Like in the last one?
Which equation? What?
Which of those three like do we actually need?
Well, they're sequential. It's just in the development of the final form. I mean, what I'm trying to tell you is this is how you get where we're going. You have to do them sequentially. Do you remember the next step, anybody? Looking back in your notes. All right, it's setting, remember I said that the only way this can be true is if this is a constant. Do you remember that? Right? And this is a constant. So I'm going to call it x double prime over x minus beta x squared. I'm going to call y double prime over y minus beta y squared. And I'll call z double prime over z minus beta z squared. Remember in Whitworth's book, he just calls that beta. You all remember? Plus beta unguided squared equals 0. Now that's the form that you get out of there. But the key thing is that this x double prime over x is that. So you get x double prime over x is equal to minus beta x squared. Some of you remember this, right? Remember when we did it before? The function we saw for was ez, not hz. But it's the same exact steps we're taking. Then I go ahead and I said, well, this is really what? A second derivative, right, of x, functional form of x, with respect to small x squared. And then it's plus beta x squared times x equals 0. And I said that's a standard second order homogeneous differential equation. Y'all remember that? We could use Laplace transforms to solve this. We probably could do it with an integrating factor. Doesn't matter how you do it. The forms that are allowable here are x. These are the solutions. Can be either some sine of beta x times x, or it can be a cosine of beta x times x. One of these two forms. Now we've got to figure out which one. Here's where the difference lies. I mean, the solution, if you put this in there for x, you can put a scaling factor in front of it. It'll solve the zero. Double derivative on a sine is minus the sine, beta x, but then you get the beta squared in front of it, beta x squared in front, and it'll cancel out, okay? Y'all with, how many see that these two are solutions to that differential equation? You're engineers, you should see this one, right? Plus, they are. Either one, cosine or sine. How do you choose which one? Here's how. This HZ is a magnetic field. This is a boundary condition and you're not familiar with it yet. I'm about to tell you, so it's important. And you will be asked questions relative to this, so just be aware. All right, if you have a conducting surface like such, if this is a perfect conductor, and we take a look at the H field on a perfect conductor surface, HZ is not zero, all right? H tan 1 is equal to H tan 2, but it is not zero. Do y'all follow me on this one? The E field is zero, but not the H field. What happens is, if this is the normal direction, if I take the derivative of HZ with respect to the normal direction, it is zero. Now, what it means is the H field is a relative maximum or a minimum. This is the tangent H field at the boundary if it's a perfect conductor. Do y'all hear me on that? It generates a surface current, it stabilizes it. So it will always be a relative maximum or minimum, which means the derivative of that H field, it's tangent to the surface with respect to the normal direction, is zero. Now, in Wentworth's book, he discusses this, but he doesn't go into depth. It's a little different, because you're used to seeing either H or E is equal to zero, or the E field or the H field is equal to, the H field on one side is equal to the H field on the other side. Do y'all remember that? But remember, when you had a perfect conducting slab with currents, the H field wasn't zero. Do you remember you did that cross product to find the value of the H field? All right, well, and it wasn't. And what you didn't learn in electrostatics is the derivative of the H field with respect to the normal direction is zero. That's the key. Now think about this for a second. If I take the sine and I take a derivative, I'll get a cosine, right? Well, the cosine can't be zero when x is zero. I mean, I didn't say this exactly, but when you have these things, right? If you have an H field in the z direction, if you think about a waveguide like this, where this is the z direction and the H field we're solving for is HZ, it means on this surface, it's tangent. Y'all with me? On this edge, it's in the HZ, because the rectangular guide, I'm trying to show you going right into the board, so I have to do it like this. HZ has to be what? The derivative with respect to the normal. On this, all these edges have to be equal to zero. Means around here, the derivative with respect to y has to be zero, because y would be the normal. Here, the derivative with respect to x has to be normal. Y'all with me? Just appreciate what I'm trying to say. Well, if I take a derivative of a sine, I get a cosine, and I know they won't be zero at x equals zero. Follow me? However, if I take a cosine and take a derivative of that, then I get a sine, and yes, they will be zero. Do y'all follow me on that, class? Now, that's the ultimate reason why, for a TE mode, you're going to have solutions that are cosine. Let me just write it down for you. Now, y'all know, I'm going to write that equation. I've got it for x, right? You know I'm going to do the same thing for y, make this sub y, right? Everybody, can you follow me on this? I'm going to do that, and then for the z, when I get the z form of it, it'll have the e to the plus or minus j beta z times it. I'm just telling you what will happen. Here's the net result, so I don't have to bore you too much, and I can get to what I really want. After all is said and done, this is in Wentworth's book. That's the reason for it. It's important that you at least appreciate the reason. You find that hz is equal to some h naught. Again, that's a scalar variable. We don't know what it is. And then it's going to be times cosine of n pi over ax, cosine of n pi over b times y. Same exact form, only cosines, not sine. And it will have the same actual propagation plus, or actually minus plus, J beta Z times Z. Here, again, beta Z, right there, is Wentworth's beta, and that's equal to omega square root of mu epsilon right there, and then it's times K, where K is equal to the square root of 1 minus FC over F squared. And remember, for propagation, your actual operational frequency has to be above the cutoff. Are you with me on this, class? No. Yes?
Is that positive JBZ?
Well, I put plus or minus, but to be frank about it, for everything we're concerning ourselves with, it'll have that minus because it'll be going in the plus Z direction. When you get reflections, then you would have the plus J beta Z. All right, remember that only thing that that sign does is tell you the direction of propagation. That's it. Okay, class? All right, now, that said, that doesn't this doesn't do much for you. Right? All right, we got phase velocity, that's nice. We've got beta, we've got the cutoff, that's nice too. But what really happens that's of interest to you, and it's called the characteristic impedance of the guide. This is important. This you write down. And I'm going to start with TE mode. I'm going to erase this. Here's where it gets really good. So, make sure you put TE. This is true for TE. Now, when you take a look at a waveguide impedance, and Z, and it would be Z for the TE mode. This is the impedance for the transverse electric. Remember, in general, when we talked about impedance, it was equal to square root of mu over epsilon, wasn't it? That's for free space. It's the ratio of E to H in free space, right? For a propagating wave. Do y'all remember that? I'm making sure. Remember, it's 120 pi. That's the thing I'm trying to make sure everybody understands. Well, when you're talking about ZETE, you're talking about the impedance that the waveguide has, or everything has inside that waveguide, to a wave flowing down the guide in a certain mode. Do y'all follow me? What it really tells you is the ratio of the E to the H field inside the guide, but it'll be the cross-sectional, it'll be the impedance of the cross-sectional electric and magnetic field. So this could be either EX over HY. They have to be perpendicular to one another, and you can't have a Z component. Or it'll be EY to HX. And they will be the same. And in any case, for TE mode, it will be equal to eta of free space inside the guide divided by K. Now, eta is equal to the square root of mu over epsilon, which is really 120 pi times square root of mu relative over epsilon relative of the dielectric material in the guide. This is the impedance for the, I'm supposed to write it in. AU Pharmacy, I left them a message when I could get my COVID test last night. Just getting back to me. All right. Anyway, I don't know if you've had that problem before. Has anybody ever left a message for a callback at the pharmacy or at any of these COVID testing centers? Well, if you get it within a week, you're probably lucky. Anyway, so that's the impedance. Now, what do you notice about this impedance? Remember, it's the ratio of E to H. Okay, that's the one thing that becomes important, and here's why. Because when you feed a guide, and you're going to feed it, we'll show you how to do it in the TE mode, your guide impedance tells you what your characteristic impedance is for the thing you're matching. You all remember matching impedances? Your source impedance has to be low. So that's why this is important. Now remember what K is, right? K is just equal to square root of 1 minus F C over F squared, right? It's less than or equal to 1 always. I mean, if you get an imaginary value, you're not propagating anything, all right? If all of a sudden FC over F is greater than 1, then you're below cutoff and nothing works. Got me on that, class? The whole thing is a wash. But it really says it's greater than 120 pi. Do you all follow me for TE mode? Now, if you wanted the TM mode, same deal. It's equal to the ratio of EX over HY. And I put magnitudes here because I don't want to fuss with the negatives. Is equal to the ratio of EY over HX. And that's equal to eta, but it's times K. So at cutoff, once you write that, I want to make a couple comments. At cutoff, K goes to 0. Y'all follow me? Whatever mode. It's the 1-ohm mode, and you're at the cutoff frequency for the 1-ohm mode. Then K goes to 0 means this impedance goes to infinity. Y'all see that? This impedance goes to 0. All right? In general, the TM mode's impedance is less than the characteristic impedance of free space. And in general, the TE modes is greater than the characteristic impedance of free space. Just something to keep in mind, okay? So now we have, I've shown you the velocity of propagation. I showed you how to get cutoff. I showed you how to calculate characteristic impedance. Now the next thing is going to be, I mean, I'll do some of Wentworth's problems, but they're really just turn to crank, tell me what modes occur, right? He gives you dimensions. There's nothing there that's really applicable to something you would do in the real world. Here's what you do in the real world. It's not this book. I'll give you problems like this. And I'll show you why it's important. Well, what did you use transmissions lines for? I mean, think about this. How are you familiar with coax cable and what applications?
Like how many?
Well, yeah, but I mean, in the practical sense, how many have cable coming in for your internet or your TV or both in your apartment or whatever? Don't you? Yeah, that's usually 75 ohm cable, right, that comes in there. It communicates, really, it's communication bands. It's wideband frequencies come in there, and they, parses them in terms of either the internet or TV and phone in some cases, right? So really, you have a huge amount of information coming in there. But that's still at relatively, quote, low frequencies. With microwave stuff, you can get a whole lot more information. It's at a much higher frequency, typically gigahertz, right? And the thing is, coax cable doesn't work well at microwave frequencies. It's too lossy. Everything will get attenuated. You won't have any energy left. So they put coax cable. And then at really high frequency, they use fiber optics, right? They use fiber optics, and they're light packets. They're really not even standard type. You don't do waveguide analysis with fiber optic cable. Not like this. They send out packets of photons. And it's a different type of analysis. But when you're talking about waveguides for high frequency applications, they replace transmission. That's what I'm getting at. So how do they replace it? Well, just think about it. Before, if you had a source, you're going to have a source impedance usually, right? I'll just call it RS. That's some source, resistance. Y'all follow me on that? Maybe 20 ohms, maybe 5 ohms, you don't know. But it's a source resistance that everything has something like that. It's an internal resistance to source. Then this thing used to connect to a coax cable or transmission line. It's still going to connect to something. Now it's a waveguide. All right? And I'm not going to show you how it connects, because the way it connects is through a little antenna here that comes later when we get to antenna engineering. And the placement of that antenna and the size of it is critical, but that's later on. We haven't done antennas yet. Just realize, I'm just showing you this connected to a waveguide. This waveguide has some impedance. And I'm going to start by saying it's TE impedance. And then it has a load. And that can be anything. This waveguide has a certain length, L, right? It has given cross-sectional dimensions. It has a given mu and epsilon inside there. I'm just showing you the cross-section of that guide. And a common thing that you would want to know is what is the voltage developed at the load? All right, what is the current developed at the load? And how much power, average power, is used by the load? Those are three things that make sense asking. So here's how you do it. Start by remembering how you did it when you did transmission line problems. Remember for transmission line problems, and I'm going to erase this here. The way you really did it is, and I'm going to go ahead and write the crazy equation. I'm not going to give you Smith-Sharp problems here. That would be a little much. Remember before, what you found is that if it was a transmission line, then there would be an input impedance right there. And the input impedance, please write this down. The input impedance right there would be some Z naught times Z load plus J, right, times Z naught times the tangent of beta times L over Do you all remember that? How many do? I'll give that to you. Kind of, sort of. I mean, it should at least jog your memory. You've seen it, right? Here's what happens to that equation when we have a waveguide. You see that Z naught? Now that becomes Z naught for the TE or TM modes, as I showed you before. Remember, I said that Z TE was equal to really what? Eta naught over K, and ZTM was equal to eta, real, maybe not eta naught, just eta times K, right? Remember that? Now that replaces that, and that. Your load is your load, whatever it is, 50 ohms, 50 plus J, 30, could be any of that. You all with me? It's just the value. The beta here becomes beta Z. All right? And again, what is beta Z? Well, it's equal to beta unguided, right? Times K. Y'all with me on this class? L is L. Can everybody follow me on this class? So you can see there are two things that are altered. The characteristic impedance is no longer just some Z naught that you read off a chart. You have to calculate it for a given frequency. You all follow me on that? You're usually in the 1 ohm mode. I'll just level with you. Any problem I give you will be 1 ohm mode. I'm not going to give you a Whitworth problem. It comes up with a mode that nobody uses and then asks you stuff. No, it'll be 1 ohm mode because that's always what they use. But there's a maximum frequency you can use a 1 ohm mode at that I will ask about. The beta there is beta Z. All right. And to be frank about it, that's the big deal. Because look, if I have this, do you remember how if I have a source voltage, how I find voltage at the load? How many do? I'm going to go through this. You do? Good. What we had to do, gets a little weird. We say the input impedance right here is this, right? Remember that? So now we look at the circuit, and we look at this circuit. We have VS, then you have RS, that could be ZS. And then you have some, and I'll just put it like this, a block here. I'll just call it ZN, right? And then you were taught you find this voltage. Whitworth's book called that V prime. How many remember doing that? All right, V prime was equal to simply VS times ZN over ZN plus RS, right? How many remember that? All right, here's something I didn't say. Now, the electric field on here, or really the voltage inside of here, you can call it a voltage. In here, the voltage as a function of Z is some V0 plus times e to the minus j, and it will be beta Z times Z. Then it's plus the reflection coefficient at the load times e to the, or minus j beta Z times Z, plus j beta Z times Z. Y'all remember that? How many do? Right? That was the standard equation for a wave that's either traveling in a positive or negative direction. And here gamma L is equal to what? It's the reflection coefficient at the load, which is ZL minus Z naught TE, right? Over ZL plus Z naught TE. You with me? You remember reflection coefficients at the load? It's always impedance you're going into minus the impedance you came from. Now the impedance you're coming from is going to have the Z naught TE. It will not be just 377, or 120 pi. Follow me? All right, so that's the equation. And if you remember this V prime here, now just listen please. What does that V prime signify? That's the voltage right here, right? Just on the inside of that coax scrub, the waveguide. That voltage is a summation of the reflected and the forward-going wave, right? So what I do is this, I take this right here, and I say that V prime, which is this value, is equal to V naught plus times e to the minus j beta Z times Z. But now Z is L, isn't it? And actually the way we do this, about out of time. Usually they call this the Z-axis. This is 0. So this point right here is Z equals minus L because the waveguide is L long. Do you remember for transmission lines, that was the negative value of Z, right? Where it's fed. So when you put that in there, it makes this be equal to plus J beta Z times L. And then it's going to be plus the reflection coefficient at the load times e to the minus j beta Z times L. Now look, do y'all agree with this? Right? We've got V prime right there. Please make sure you see this. This isn't in the book. Now, can we get V0? Yes. We can say that V0 plus will be equal to V prime divided by e to the plus j beta Z times Z plus the reflection coefficient e to the minus j beta Z times, or not Z times L, pardon me. L. And the reason the sign changes here is because Z becomes minus L. Now I have V0 plus. Last thing before we leave, now I can say that the voltage at the load is simply equal to that V0 plus that I calculated right there. And since it's at Z equals 0, it's just 1 plus the reflection coefficient. Are you with me? You remember that from before? The way we're doing it? You're going to see this over and over again, all this stuff. So that's how you get the voltage at the load. How would I get the current at the load? Just for completeness. Anyway.
Divide by
ZL, right? If I got voltage, if I want current, I divide by impedance. How would I get power? You could take 1/2 V times I conjugate, right? It has to be the conjugate of I. Correct, class? Technically, you take the real part of that, but it'll always be real. I'll ask you some things about this. This is not in this book, but this is an application of real world. It's really waveguide or microwave analysis. Follow me? I'll give you some more stuff on this to work on. We'll pick it on Monday. So you're worried about your quiz. I'm not going to do one Monday. I think I may wait till the following Friday, but I don't know. I'm going to do something. I haven't figured it out yet, all right? I'm trying to be fair to everybody about this. Again, stay safe. And if I'm going to give you homework, so on Monday, please come, okay?